I'm taking up the investigation on 3.2, which is reading and interpreting some quadratic relationships. For example, number 1, the graph is given, and you just kind of have to estimate where the values are. So at time 0, the ball is down on the ground, right down here, and ball goes up in the air, and as it goes in the air, the height increases, and the ball at the same time is traveling downwards down the field when it's been kicked. So this is just tracking its height compared to how far down the field it's been kicked. So the maximum height occurs right here, and I estimated that to be about 62.5 meters. As long as you said it was more than 60 and less than 65, and ideally somewhere in between those things, that would be your best option. So like a 62 or a 63 would be fine as well. How far down the field was the ball when it reached that maximum height? So if I look at this, it looks like I'm 25 meters downfield when the ball is at its maximum height. And then how far down the field was the ball when it landed? The height is 0 right here. So where the height is 0 is where the ball is landing. So that's how we know it's 50 meters down the field. Number 2 is the rocket being shot into the air. And what we have is the height in meters of the rocket since being fired. And my picture accidentally cut off the bottom of this graph, unfortunately. How high did the rocket go? We're looking at this top point here, and I estimated that to be 247. I would say anything between like 240 and 250, well, less than 250. I'd probably accept as answers. As long as they're reasonable, when you're reading from a graph like this, you just kind of have to ballpark it. And then what time did it reach the maximum height? If you follow that down to where that axis was, it matches up with 7 seconds after being fired. So along the bottom here we have time. So this is our time axis. And then we check to see when it hits, how long it's in the air. We're looking for this point where the height becomes 0 again. And a height of 0 means it's at the ground and it's no longer in the air. So that was at 14 seconds. Now with both these graphs, one thing to really note that's important about these kinds of curves is we have symmetry happening with them. So if I look at my example number 1, I had that vertical line that I drew in right here at the high point. Every point on either side of that, horizontally on either side, is equal distance from that line, and that vertical line that cuts it exactly in half is called the axis of symmetry. We're going to take a note on that in a bit. You'll notice that the x-intercept down here and the x-intercept are equal distance from that axis of symmetry. So this is 25 meters in, and this is 25 meters across here as well. So that's going to be a really important idea throughout this unit and the other quadratic units that we do. So at the bottom here we have these which are called x-intercepts, or also known as the zeros of our graph. So these kinds of curves will be symmetrical. All right, moving to example. The ball is thrown upward, and I asked you to graph this using technology, so you could use your Desmos for this. Now, when I did this, I actually just did y equals, so instead of h, I replaced the h with a y on Desmos. You could actually go in and change the letter using the alphabet key and change them to h's and t's, but I did use a y and an x. I did an x squared plus the 1, dang it, squared plus the 15x plus 1.5, and I put that into my Desmos, and then I was able to graph it. The relationship between time and height, we ended up with this U-shaped curve. The ball first increases in height to a maximum, and then it decreases again. And when you look at your graph, we've got some important pieces of information here. The maximum height of the ball, so looking at the top of the parabola, this is what we call this kind of graph. The height of the ball, its maximum height was 12.98, and you get that just by tapping on Desmos where you think that maximum is, and if you actually tap it a second time, then it will come up with the coordinates for that point. And then the time is this axis. So we've got height vertically and the time horizontally. That height matched up with a time of 1.531 seconds, depending on how many digits, how many decimal places you took that to. Now, how can you tell the initial height of the ball, besides the fact that it tells you in the equation? How can you tell that the initial height of the ball is 1.5 meters? Well, if you look at your Desmos, if you look at where time is equal to 0, where time is 0, in other words, where you have that y-intercept, that y-intercept value is 1.5. So that is our initial height. Anytime you want the starting height or initial value, you're looking at letting your independent variable equaling 0. Okay. Now, after how many seconds does the ball reach the ground? We're looking for this x-intercept, or the zeros. So this one is the one we want to find, and if you tap on it in Desmos, it gives you the 3.15 or 16 or 158, depends on how many decimal places that you're taking. So that's how many seconds it takes to hit the ground, because the height's back at 0 again. So hitting the ground, we're really looking at, reaching the ground, we're looking at things like our x-intercepts, where y is equal to 0. And as we do application questions, these ideas become very important. So if we can introduce it graphically now when we do the algebra part, hopefully this will make more sense. Okay, next example. All right, cost of operating the machine is given by this equation. So C is cost and N is the number of minutes in use. So we need the minimum. We want the minimum cost of operating. So we want the lowest point. And I found on Desmos, using my y equals and my x for my n's. So y for my c and x is for the n's. I got 15, 170, and that 15 goes with the x, which is really n. So how long is the n? It's the number of minutes. So that's going to be 15 minutes for it to reach the minimum cost. And then the minimum cost itself, it's the y coordinate of this lowest point. That lowest point is called the vertex, is 170. So lots of vocabulary for this unit that we need to learn, and that's really where we're going with this lesson today. All of these above examples had graphs that were U-shaped. Okay, they all look like this, or that last one was one that, sorry, they all were opening down, my second one. The last one was actually the one that was opening up. These graphs, when you graph it, it's called a parabola. And the algebraic model that represents them are called quadratic relations. Okay, hopefully you've done example 5. If not, like, skip what I've got on here, or don't look at it. Graph them, see which ones that are linear, underline the ones that are linear, circle the ones that are quadratic, and then put an X through the ones that are neither. Okay, and then you can check. Okay, when I did mine, I found these as my results, and I want to talk about a couple of these specifically. We know that we have lines when we have ones on our x's and y variables. So these are linears, and I had other things in all my other equations that made those ones not linear. Now I have some quadratics here. I notice I have an x and an x squared term. Here I have an x squared and a constant. Here I have an x squared and I have a number. All of these just have a single y to the 1 in them. Here's a y to the 1. Now this one is a little bit different in terms of these other ones. Like, this almost looks like my x's are just exponent 1s. But actually, if you were to do the multiplication of these two brackets, you'd end up with an x squared on it. In fact, if you were to expand and simplify that equation, if you were to multiply it out, collect like terms, for that one you get y equals -3 x squared plus 12x plus 36. So if you were to put this equation into Desmos, this new one that I just wrote, the -3x squared plus 12x plus 36, if you put that in Desmos along with this one that I gave you here, you should get an identical graph. The two parabolas should lie on top of each other because these two are equivalent to each other. So I notice on this second one, this one that I wrote here, I now have an x squared term. I have a y to the 1, I have an x squared, an x, and a number. Now similarly, the bottom one here, this one, doesn't look like it has an x squared, but again, if I were to actually be nice and write this out twice, like square this binomial here, I would end up with something with an x squared in it. And I would get y equals 2x squared minus 12x plus 25. So if I were to graph the new equation that I just wrote along with the original one here, they should be the same parabola again. And again, I have an x squared term. So the key idea behind what parabolas are is you have to have a y to the 1, but you have to have an x squared when you write it out in this format that you've expanded and simplified. Okay, where you've done all the multiplication. Now these other ones are not going to be parabolas. This one's not because it has a y squared along with the x squared, and you cannot have y squared. This one is not because you can't have that x squared on the bottom of a fraction. It gives you another weird graph that you talk about a little bit in grade 11, but definitely a lot in advanced functions in grade 12. This one does not work because it has a y squared. This one has the x as an exponent, and x cannot be an exponent to be a parabola. And this one, if you were to be nice and actually expand and simplify this, you're going to end up with an x cubed in that one, and that makes that one not be a quadratic or a parabola. So in summary, I had written down here that linear, to be linear, our x and y have exponents of 1 on them. No exponent written means the exponent is a 1. That means it's going to be linear. We knew that probably, or we should have known that from grade 9 last year. A quadratic, this is the key here. The y must have an exponent of 1. X has an exponent of 2 when the equation is written in standard form, when it's multiplied out. So you can't have any brackets in it. It has to look like this. We're going to have a y equals ax squared plus bx. So the a and the b are just numbers. The x's are our variables, and then plus c. Again, c is just some number. So if it's in that format where the x, the highest power of x is a 2, then it's going to be quadratic. Now, example number 7, you're asked to graph them and decide if they're opening up or opening down, and then number 8 is asking you to see if you can figure out the connection. I'm going to go forward to that. If you haven't done that, put it on pause and try it, and then go on. Okay, I found my results were as written up here with example number 7. If I were to actually compare all of these, if I look at the value in front of the x squared, this one's positive, this one's a negative. Positive, if you're positive, you're happy, you're smiling, you're opening up. If you're negative, you're down, you're frowning, your smile goes upside down. Okay, this one, if I wrote that out, I would get an x squared, but it's going to be a positive. That's why it's opening up. This one's a negative in front of x squared, it's opening down. Positive in front of x squared, opening up. Positive in front of x squared, opening up. Negative in front of x squared opens down. This will be a negative in front of these getting multiplied, which is an x squared. That's an opening down. This one, x times x, will be my x squared, and it's a positive 2 in front, so it's opening up. So if the number in front of the x squared is positive, the graph opens up. If it's negative, it's opening down.